Hello everyone and welcome to today's webinar on the H-Cube Advance. My name is Nando Arcania and I work as the Director of Chemistry here at ThalesNano. And I would like to welcome you on today's webinar. It will be my job today to explain how the H-Cube Advance can revolutionize your chemical synthesis, especially hydrogenations. Today's webinar will consist of 5 individual parts. First, we will have a look at a little bit of history with a special emphasis on the evolution of hydrogenation in continuous flow. And we will have a look at how we have achieved the production of the H-Cube Advance, and especially the H-Cube series, how it led to the H-Cube Advance. Secondly, we will have a look at the instrument itself, discussing its key features and what are the upgrades to the previous generation equipments. And then thirdly, we'll have a look at a few applications. So these are real chemical experiments that were performed on the system. And then after that, the PowerPoint presentation will be over and we will move over to the lab where we will give you a live demonstration of the actual instrument itself during its working operation. And then finally, we will conclude with a live Q&A session where you will be able to ask your questions. So let's jump into the first chapter, which is going to be the historical overview of hydrogenations and especially continuous flow equipment. So let's start by discussing the batch hydrogenation protocols. So traditional batch hydrogenations, which is still done by many labs today, involves hydrogen cylinders and highly pressurized vessels. So this carries a bit of risks with itself. It's got safety concerns as well, especially because of the combustibility of hydrogen and the difficulties that rise with scale up. We'll discuss all of these issues in a little bit more detail later. But it requires highly trained personnel to perform conventional batch hydrogenations still to this day. During the design of the continuous flow hydrogenation equipment, we bore these difficulties in mind, and we designed a system that would be able to circumvent these difficulties. Of course, working with hydrogen is always going to be inherently hazardous because it's a flammable gas. It has a combustible concentration of 4%, so if it mixes with air, such a low concentration as 4% of volumetric percentage in the air will already form an explosive mixture. And that's why the companies and the research facilities are trying to move away from hydrogen cylinders and are always looking for more safe alternatives on how to perform hydrogenations. And then comes the second problem, which is the catalyst. So hydrogenations often require noble metal catalysis, and many of them are actually pyrophoric. So this will increase the danger because it has to come into contact with the hydrogen. So that will even further raise some safety issues and make the traditional batch protocols even more undesired for the user. And then comes the difficulty of scaling up these batch experiments. It's never easy to scale up any batch protocol because of the mixing, and the heat transfer becomes less and less efficient as you scale up your reactions. So this is especially dangerous in the case of hydrogenations because of the mixing. The hydrogen has to dissolve or at least mix together very well with your liquids and your solid materials. And if the reaction is, for example, exothermic, which hydrogenations often are, you get hotspot formations or thermal runaway phenomenon in your reaction mixtures. So it's never easy to scale up a batch experiment. And that's why flow chemistry is even more advantageous. We will also discuss this in a little bit more detail because scale up becomes much more convenient and much more safe. So what is the advantage of the H-Cube series? So this is where we started approximately 22 years ago. We had this idea that how can we provide a safe alternative to conventional batch hydrogenations? And the most important answer was to produce the hydrogen on demand. So that means we are using water electrolysis to generate hydrogen and oxygen gas from the water. And for this, we have a patented electrolysis cell that's built into all of our instruments. So this is how the H-Cube series has started. The gases are generated separately, so the geometry of the cell allows these gases to never mix together, and the oxygen can be vented out on the back of the instrument so that it never has the opportunity to mix back together with the hydrogen gas. And then the hydrogen goes through a series of purification instruments internally within the H-cube. For example, water separation, so therefore we can provide at least 99.9% pure hydrogen gas as a result. And that was the major breakthrough that happened 22 years ago with our first generation of our H-cubes, which allowed continuous flow hydrogenation for the first time. And the main advantage of this technology is that you don't have to store any excess hydrogen, for example, in cylinders or built-in gas lines into your fume hood. And the second advantage is that you are only generating as much hydrogen as you are using in your reaction. So this is called on-demand hydrogen generation, and it makes the technology a whole lot safer because you don't need to store vast amount of hydrogen, and the amount of hydrogen that is generated and stored within the cell itself is absolutely tiny. So you don't get any explosive hazards or overpressure hazards, or just you never get any chance to form an explosive mixture with the air, even if the hydrogen is released into your fume hood or your working environment. And that results, of course, in a lot of safety. So the improved safety features, which makes the continuous flow hydrogenations a lot more user-friendly compared to the batch protocols. So here you can see the three most important members of the ThalesNano's H-Cube series. The H-Cube, the first H-Cube that was developed about 20 years ago, also received the R&D Top 100 award in the US in 2005. And as of this day, we can present approximately 1,000, it's even surpassed 1,000 publications that were done in our instrument. And the vast majority of these publications are using some member of the H-Cube family to perform their experiments. So we are really proud of this achievement, and we are very proud of our users that had a lot of success in synthetic chemistry using continuous flow hydrogenations. As of today, we still have three members of the H-Cube series available on the market, starting from the H-Cube Mini Plus, which is one of our simplest instruments. It's designed for entry-level hydrogenations, so if you are not really interested in large gram-scale productions, and also you are not interested in thorough and detailed optimization of your protocols, you just want a yes/no answer. Can I do this experiment in continuous flow? Then we recommend the H-Cube Mini Plus because it's very, very simple to learn. It takes about half an hour to familiarize yourself with how this instrument works. It literally has only 4 components. You can kind of see it on the front panel here. So 4 individual elements is included into the flow path. So very simple to learn, and the user interface, which is up here on the touch screen, is very easy and very intuitive to learn. And then we have the H-Cube Pro, which even last year was already the market leader instrument, which allows a little bit more complex experiments. It has double the hydrogen amount capacity, so it contains 2 electrolysis cells capable of producing twice as much hydrogen compared to the Mini Plus. And it's also equipped with a little bit more instruments on the front panel, so it allows you a more complex analysis and a more thorough optimization of your protocols. So if you're interested in catalyst screening or detailed parameter optimization, we recommend the H-Cube Pro, and it can also sort of double the throughput capacity compared to the Mini Plus, because it is producing twice as many hydrogen gas. So that means the amount of product that you can achieve with this instrument is no longer in the hundreds of milligrams to the gram, scale, but rather in the gram to tens of grams scale with this instrument. It's also available in Hastelloy version. So if your starting materials are corrosive, it's also possible to perform these reactions in a very safe way. And then we have the H-Cube Advance, which is, of course, today's webinar topic. And it has a few improvements compared to the H-Cube Pro, which we will have a look in detail right now. So let's jump into the second part of today's webinar, which is going to be the demonstration of the H-Cube Advance itself. We will have a look at all of the parameters and all of the availabilities that the Pro already had. We'll give you a brief recap on those as well, but then the focus is going to shift towards what's new compared to the H-Cube Pro. So the instrument can produce a little bit more hydrogen gas compared to the H-Cube Pro. So the older instrument, the previous generation instrument, was able to produce 60 milliliters of hydrogen gas per minute. And now using a next generation or a new generation of the electrolysis cell, we were able to achieve 70 milliliters of hydrogen gas per minute. So it's a slight improvement compared to the H-Cube Pro. And also the temperature range has been extended because the H-Cube Pro used to be able to cool down the reaction mixtures to 10 degrees C. And we have improved this cooling with a new generation Peltier element as well. And now it can achieve 0 degrees as well. However, the most important novelty of the H-Cube Advance compared to the Pro is the built-in mass flow controller. So it was already possible to use external gases with the H-Cube Pro as well, but it was not a built-in feature. You had to purchase separate mass flow controllers, individual standalone instruments, or our own gas module to inject and insert the external gas. And now you no longer have to do it. It's built into the system. And it's also responsible for accurately dosing the hydrogen. So if you are generating hydrogen within the instrument from the electrolysis cell, it too goes through the mass flow controller, allowing for a much more precise injection of the hydrogen gas. But if you're using an external gas source, that also goes through the mass flow controller. And now you have the option of injecting 14 different gases, for example, oxygen, nitrogen, carbon monoxide and dioxides, and various nitrous oxides as well as some organic gases, for example, ethylene or ethane, to do organic synthesis with other gases rather than not just hydrogen. It's also got a new user interface, which has a modern look. You will be able to see that today during the live demonstration. It became a lot more intuitive and a lot more simple to learn compared to the H-Cube Pro. It has the same capabilities in terms of making the optimizations a lot smoother. However, it became less complicated to do that. So user friendliness, I think, has improved really nicely compared to the Pro. One thing that is similar to the between the Pro and the Advance is the purity of the hydrogen gas. It's producing 99.9% pure hydrogen thanks to the water separation technique that we incorporated into the system. And then the H-Cube Advance contains also a water purifier cartridge that is filled with an ion exchange resin. So this is useful for keeping the conductivity of the water down to a acceptable level, because water will pick up carbon dioxide and other contaminants from the air, and that slowly, gradually increases its conductivity, which has the potential of damaging the electrolysis cell. And in order to circumvent this problem, we have integrated a cartridge that has a mixed bed ion exchange resin filled into it, and the water will flow through this cartridge before it enters the electrolysis cell, and that will grant a good quality of the water for a couple of months, and avoid basically to increase the longevity of the cell. That's what it's good for. I already mentioned the second generation of the water electrolysis cell. So now this is what we use inside our H-Cube Advance. and this grants a longer cell life. That also helps, by the way, from the water purifier cartridge. That's good for the same thing. But the next generation of the construction of the electrolysis cell is also designed for a longer cell life. And I've already mentioned the higher gas flow rate, so now we can do 70 milliliters instead of 60, and lower maintenance cost is also an advantage. We are also working right now on some development projects that will involve AI integration into the system. So we are planning to use machine learning algorithms to teach the software a few tricks that we already know from the previous past 20 years of experience. So let's briefly discuss the user interface. It's got actually two modes of operation. We've got the manual and the automated mode. In the manual mode, you can sort of individually start each segment of the, or each part of the system, including the pump, the hydrogen injection. You can start the heating or the cooling of the reactor zone, and then influence the pressure, the reactor zone pressure. So each of these four parts can be operated individually using the manual mode, or you can just go to the automated screen and set up each parameter, enter each parameter in a digital form. You can even set up pre-washing and post-washing times, reaction times, and then you just press start, and all the valves and all the controls will happen automatically if you do that. One crucial advantage of the H-Cube Advance compared to the H-Cube Pro is the ability to incorporate this instrument with our other reactor types. So we've got a software that we call the THS reaction software, which is responsible for controlling all of our other instruments. For example, here you can see a Phoenix H-Genie setup, which is our scale-up system, once again designed for continuous flow hydrogenations. But rather than using the gram scale, this system can now produce a kilogram amount of products per day. And this fleet of systems, or this complex systems, is operated from this THS reaction software. And the advantage of the H-Cube Advance is that it is the ability to communicate with this software. So you can incorporate a small-scale synthetic platform into your fleets, and in parallel to that, you can run the large-scale system from the same user interface as well. The software can also cope with third-party instruments, for example, a lot of HPLC pumps and an autosampler, which is an automated liquid handler, is very useful for the automation of injection of samples, liquid samples, and collection of the products. So if you are doing a library synthesis or screening of parameters and optimization of the conditions of the reaction, the autosampler can be very useful, and the software to make your life a whole lot easier by allowing you to program and automate your step of reaction. So here we would like to demonstrate just very briefly one possible example of our fleets. So fleet is kind of a new concept in flow chemistry, and we like to define instrument fleets as two parallel synthetic platforms that are doing either separate things, completely separate things, for example, two large-scale synthesis. So this can be two complete Phoenix Genie platforms or two H-Cube Advances that are doing completely different types of reactions. However, they can be also interlinked with one another. And this is the example that we show on this slide. On this top setup, you can see a small scale synthetic platform, which is which is responsible for the optimization of a nitro reduction. So it's equipped with an autosampler that's doing the injection of the sample as well as the collection of the product. So the starting material is injected, and using a Union T, we can inject this to the beginning of the H-Cube Advance system, and it then goes through the whole reactor. And then if we switch this valve to the product collection, we have incorporated an inline analysis step into this synthetic setup using the SpinSolve NMR spectrometer from Magritech, and we used fluorine-19 NMR spectroscopy to monitor the conversion of the nitro compound. And then immediately after that, we were able to use all of these data that was collected by this system to do the optimization of the second step. So this is the subsystem number 2, which is a scale-up platform. It involves 2 phoenixes and an HGenie. So that's our large-scale system, capable of producing maybe kilograms of product per day. And you can see this is a 2-step reaction, because we first make the morpholine substituted nitro compound by mixing these 2 reagents together. And it goes to the first Phoenix reactor, which is equipped with a loop, with a coil, because you don't need any solid metal catalysis for this step. And then the crude reaction mixture doesn't need any isolation at all, so you immediately carry on to the next step, which is a dilution by clean solvent. So we make a more dilute solution. We mix this crude mixture together with the hydrogen that's coming from the HGenie in this case, and then the whole gas liquid mixture is injected into a second Phoenix, which is this time equipped with a loaded catalyst column. This is where the hydrogenation of the nitro moiety happens. Then you only have to regulate the pressure of the whole system, and then you could collect the product, which is an analogous molecule to the linezolid intermediate, which is a key API molecule. So this is quite a convenient example of a reactor fleet where 2 parallel things are happening, and you can use one result to much more quickly optimize the large-scale synthesis. So let's have a look at the other further applications. So we will have a look at now some chemical reaction types that are possible in the H-cube Advance. And there are, of course, widely known applications which are really common. So if you're doing even traditional batch hydrogenations, these would be the most trivial and the most common applications. Perhaps the most important in pharmaceutical chemistry is the reduction of nitro groups, which is a very important technique to make primary amines. So this is, I think, I would say this is the most widely used reaction type in the H-cube series. This is what we have the most publications on. But that, of course, doesn't mean that this is the only type of reaction that you can do. We can do other types of reactions. For example, nitrile groups, double and triple bonds can also be reduced. By the way, triple bond reductions can also be done selectively to afford olefins by using poisoned metal catalysts as well. We have a lot of applications and a lot of publications on that topic as well. And then there are some more difficult transformations, such as the saturation of nitrogen heterocycles and also deprotections. So this is also just one example. There are other possibilities for deprotection reactions, but this one involves debenzylation of a carboxylic group. And then, of course, it undergoes also a decarboxylation. But if the benzyl group is directly connected to the nitrogen atom, we can remove that type of protecting group as well. And then we have included one example, which is, I think, the most common application that doesn't involve the use of any gas, which is the Suzuki coupling involving a boronic acid and the aryl halide to afford biaryls. But there are also many other coupling reactions besides the Suzuki Sonogashira reaction. We can do Heck reactions. We can do Ullmann type of coupling reactions also in the H-cube Advance. We just selected the Suzuki because I think it's the most important and the most common cross-coupling reaction. And now let's have a look at some of the more rare examples that are also still possible in our H-cube series. First one is carbonylation using carbon monoxide gas. So it's perfectly possible to turn off the hydrogen production from the cell in the H-cube Advance. And using the built-in mass flow controller feature of the instrument, you can connect a carbon monoxide cylinder to the H-cube Advance, and then you can do carbonylations. our CatCart technology allows to pass the gas-liquid mixture through a solid metal catalysis column, so pre-filled catalyst cartridges basically, and we offer many catalyst cartridges that will support these type of carbonylation reactions. So carbonyl insertions is a pretty interesting application that is possible in this reactor system. Perhaps a more rare variant of the nitrogen heterocycle saturation is the saturation of benzene rings. So it doesn't contain any heteroatoms, and usually these type of transformations are slightly more difficult because of the carbon atoms. The ring only contains carbon atoms, so these are considered as slightly more difficult transformations. But thanks to the wide parameter scope of the H-cube Advance, which is 150 degrees and 100 bars of hydrogen pressure, it becomes really convenient and absolutely possible to saturate even the most difficult benzene rings. Another interesting application which doesn't involve, once again, the use of hydrogen, but rather oxygen. So we only need an oxygen cylinder to do catalytic oxidations. For example, this is useful for converting alcohols and aldehydes into either carboxylic acids, or you can even stop this reaction at the aldehyde level if you are using a more selective catalyst than that. So once again, we have many synthetic examples and many publication papers on oxidations in our instruments. The Hastelloy version of the instrument also allows the use of corrosive agents. So for example, nitration becomes available or possible in continuous flow. Again, you would turn off the hydrogen production for this reaction if you are only interested in the nitration step. And then the cell itself is also capable of handling deuterium oxide heavy water to produce D2 gas in situ. So deuterium additions to double bonds becomes possible very easily in continuous flow. And you can also use deuterium exchange reactions. So that's a substitution type of reaction to synthesize isotope labeled materials as well. And finally, I would like to just briefly mention one possible application that I actually mentioned already when we talked about the fleets. So this is a more detailed slide on how we achieved the live monitoring of the dichloronitrobenzene conversion using the SpinSolve spectrometer from Magritech. So we used fluorine-19 NMR spectroscopy to monitor the conversion of this reaction. So basically the setup is already discussed previously. So this is the same setup. Injection starts from here. It's injected to this side of the reactor. It goes through the H-cube Advanced system. And then the product goes through the analysis, and then it's collected to the sample collection vials of the autosampler. And if you do that, you can monitor the conversion of the starting material, because the nitro group results in a completely different chemical shift of the fluorine atoms. So that's what you can see on the first spectrum. So this is a pure starting material. We measured the starting material spectrum by just turning off the hydrogen production and just injecting the nitro compound through the system. And then we turned on the hydrogen production and increased the conditions gradually. And we were able to monitor the decrease of the fluorine signals in the starting material. And we also detected the presence of an intermediate, which is this blue and the pink lines, which was the N-hydroxy compound. And then after increasing the conditions or parameters even further, we were able to fully convert all the starting material and all the intermediates into the desired primary amine, which is basically, you can see the top three spectra was already kind of quantitative conversion. So this is a very good example on how we can incorporate third-party instruments and inline analysis into our fleet and applications. So the H-cube Advance, we can recommend the application of this instrument for anybody that is interested in reductions and hydrogenations. Of course, the petrochemistry industry and the pharmaceuticals would be the two more common examples to that. So we've got a lot of customers from this field of area, but it can be also useful for the fine chemical industry. And then if you are synthesizing catalysts, you can do a really rapid catalyst and parameter screening and testing of catalysis batches using this H-Cube Advanced instrument. And then recently we have discovered some green chemistry applications as well. For example, the synthesis of sustainable fuels and useful chemicals from carbon dioxide, which is useful for the valorization of CO2, is also possible in a system like this. So thank you very much for attending to this first part of the webinar. And now we are going to move over to the lab, and I'm going to show you how it works and how it looks like in a real laboratory environment. Thank you. Hello and welcome to the second part of today's webinar, which is going to be the live demonstration of the equipment in a real laboratory environment. So here you can see the most basic setup of the H-Cube Advance, consisting of one HPLC pump. We are using two different starting materials, a clean solvent, this is isopropanol, and a reactant, which is going to be a nitroindole to demonstrate a real chemical experiment for you. And then we have two other flasks on the other end, one for the waste and one for the product collection. And in the middle, you can see the HPLC pump and the H-Cube Advance instrument itself. So firstly, let me briefly talk you through the front panel tubing and what's happening when you start the experiment. So the first thing that happens is there's a selector valve on the side of the instrument that allows you to select between the starting material or the solvent. Today we are going to start with the solvent to do a pre-washing and an activation of the catalyst cartridge inside. So we are going to select this side, and then the HPLC pump will carry the liquid through this tube into the selector valve, and it goes into the pump head, which is then injected through this tube to the first step inside the H-Cube Advance, which is actually a gas liquid mixer. So the electrolysis cell is located inside of the instrument. It's got an integrated water pump as well that's responsible for the constant fresh water supply of the cell. And once you start the instrument, you get an option to select between the internal hydrogen generation that will start the cell and the water pump, or the use of any external gases, which just uses the mass flow controller, and you can use the connections on the front panel tubing as well to connect a separate gas source. And that if you do that, the cell, of course, and the water pump doesn't start. Today we are using the instrument with the internal gas already selected and the pressure already built up inside the system. So you get an immediate option available to you to start injection of the hydrogen gas as well. And if you do that, the mixing of the liquid that's coming from this tube and the gas that's coming from internally happens at this point. So this is a gas liquid mixer. And then the next step on the front panel tubing is a pressure sensor. So there are two pressure measurement points within the flow path, and this is the inlet side, the inlet pressure, and that's useful because the filled catalyst columns, we like to call them the cat carts, that is short for a catalyst cartridge. If you inject gas liquid mixture through the cat carts, there's a natural phenomenon of a pressure drop, so there will be a pressure difference between the inlet side and the outlet side. And this is a characteristic parameter of flow chemistry, that any filled column will have a pressure difference between its inlet and its outlet. So it's useful to insert two different pressure measurement points to detect this fall of pressure between these 2 points. And it's just a useful information for the user. So that happens here, and after that we go to the bubble detector. So this is a see-through cell that's illuminated by a blue LED light that allows you to visualize whether the hydrogen gas has already entered the flow line or not. Of course, if the hydrogen production is turned off, you won't see any bubbles. It's possible to use the system with liquid-liquid reactions only. But if you're doing a hydrogenation, or if you are using the external gases option, you will be able to see the gas-liquid mixture in forms of bubbles passing through this little cuvette. And that's just, once again, useful information for the user that allows the visualization of the mixture that's already passing through the system or not yet. And then the next step in the flow path is the actual reactor zone. So this is a heated block, which can actually be cooled down as well. I already mentioned during the first part of the demonstration that it's capable of achieving 0 degrees at minimum and 150 degrees maximum of heating capacity. And this is also the place that holds our catalyst cartridges. If you would like to change this catalyst cartridge, for example, to do a catalyst screening experiment, all you have to do is just to unmount this little hand-tight fitting on top. You don't need any tools for this. It's perfectly possible to do by hand. And if you do that, you can use the lever to lift the cat cart and then change it to a different one. And once you do that, all you have to do is to screw back the top, and you are already ready for the next experiment or the next catalyst type. The next stop within the flow path is the pressure sensor, another pressure sensor. This is the outlet pressure sensor. So once again, this will give you the difference between the inlet and the outlet side of the catalyst cartridge, the column. And this is also what we consider to be the reaction pressure. So in flow chemistry, it's a well-known convention to define reaction pressure as the back pressure, the outlet pressure of the system. So this is what we regulate the pressure for. And then there's, of course, the pressure regulator valve itself, which is responsible for building up all the pressure within the previous steps of the system. The maximum capacity of this pressure valve is 100 bars, and therefore the electrolysis cell is capable of maintaining 130 bars because it needs to overcome the pressure drop that we already talked about. And on top of that, it needs a little bit of extra pressure as well to allow for the breakthrough of the hydrogen into the system. So there's a little bit of resistance in the gas liquid mixer, and it's not easy to inject a gas into a stream of liquids. So therefore, to overcome this difficulty, the cell needs to produce a couple of bars extra pressure compared to the liquid pressure. So that's why the cell is allowed to reach 130 bars of hydrogen pressure. That will be more than sufficient to maintain the 100 bars, which is the capacity of the instrument itself, the reactor zone. And then the last step of the flow path is a similar selector valve that you can see on the inlet side, except this one allows you to switch between the product and the waste collection. So at the moment, they are both connected to two empty flasks. And one of them is going to be our waste collection, and the other one, the product collection. So this is the starting screen that you see when you first start the instrument. This corresponds to the automatic operation mode of the instrument. So here you can see all of the parameters on the same screen. On the top, there's a line here which demonstrates the pre-washing, the priming, and the post-washing times. So you can set up individual times for how long you would like to wash the system with a clean solvent. So if you set those times, the valves that will switch between the solvent and the reactant, and also the product and waste, will automatically be switched once these set times are over. You can also set up reaction times as well, and the injection of the real starting material will be continued until this time is up. To do a manual operation of this, you just set all of the times to 0. If you do that, you control all of the valves by hand, and you decide how long you would like to wash the system for and how long you would like to inject the starting material. So underneath this timeline, the line on the top, you can see all of the other settings, including the hydrogen pressure, the flow rate of the pump, and all the reaction parameters. On the first top left-hand side, you can see an internal H2 button. So this is what I selected when I started the instrument, because you get the option of internal and external hydrogen or external gas. When I started this experiment, I selected internal hydrogen to allow for a buildup of the hydrogen pressure inside the cell. But if you click that button, you can always select the other external gas options. You get a list of 14 different gases, and that's useful for the built-in mass flow controller to accurately dose the gases according to their densities and molar masses. If you do that, there's an external gas inlet on the front panel tubing, and you can just connect to an 8-inch tube using standard connections and fittings, and you just need a gas cylinder to dose the external gases from. You can also operate the pump using the second window of the main screen, so you don't have to use the manual buttons of the pump. It's perfectly possible to operate the pump using the automated screen as well. And you can also control the mass flow controller, so you are dosing the gas and the liquid from pretty much the same place at the same time. And then on the right-hand side, you can see the pressure and the temperature settings. So that's what's controlling the heating or the cooling within the cart zone, the catalyst, the reaction zone, and also the pressure that I already mentioned is the back pressure regulator. So, for example, just to demonstrate, I can click on the temperature button and I can put 100 degrees, and if you press enter, the value will appear on that little window. And if you press the big start button, all of these parameters that you previously set will automatically start to build up. The second function of the touchscreen is the graph function. So this is the screen that will be able to monitor all the reaction parameters live. It takes one data point every second. So it's very useful to visualize all the buildup of pressures and temperatures. And you can save this data for a later analysis. So it actually works as a lab note function as well. And on the side, you can select or deselect which parameters you would like to be recorded. So if you are not interested in the gas flow rate, for example, you can always deselect it from the list and just only have a look at the most important parameters for your experiment. You can also zoom in and out on the axis as well. So if you are interested in only a particular region of the graphs, it's also possible to set it up. Moving on to the third type of screen within the instrument. This is the manual operation screen. So this screen will allow you to operate each of the individual elements all by itself. So instead of setting all the parameters all at once and pressing start, you can now individually start each of the functions. So on top, you can see the pump itself. If you click on this window, there will be a number panel appearing, and you can set the flow rate of the pump. Underneath that, you've got the mass flow controller. So this is responsible for dosing the gas. Once again, you get the option, the same list, to select any external gases, but right now it's set to internal hydrogen. So I'm producing the hydrogen gas from water electrolysis in this case. And the number panel allows you to set up the flow rate. And then the next button is the reactor temperature. And it also displays the inlet pressure. That's not a settable parameter, but it's also just a display of the inlet pressure. And then the last window is the back pressure. This time you can set this. This is considered to be equal to the reaction pressure. And you can set any value between 0 and 100 bars. The selector valves can also be operated manually. So on the left-hand side, you can get a switch between the solvent and the reactant. And on the other side, the product side, you get a selection between the waste and the product. So next, we are going to have a look at how the instrument functions. So I'm in the manual operation mode. I've got the solvent side selected, so I want to make sure that I start off with injecting a clean solvent into the system. That's good for the activation of the catalyst. If you add hydrogen gas to it, that's often a common trick that we teach to our customers to do an activation cycle or an activation period before the experiment. If you insert clean liquids or clean solvent plus hydrogen mixture for 10 minutes through the cat cart, that will allow the activation of the catalyst, and it is very good for the catalyst lifetime, and it allows you to achieve a lot more yields and conversion. So in order to do that, the first thing I'm going to do is to click on the pump window and I'm going to put 1000 microliters per minute, which is 1 milliliter per minute, the most common setting for a system of this size. And I'm just going to press the on button, and you can immediately see that there's a dotted line moving around. There's an animation that indicates that it's pumping the liquid through the solvent flask, the clean solvent flask. And the next thing I would like to do is to set up my parameters, my conditions for the experiment, which for my case is going to be 50 bars of pressure and 100 bars of temperature. And it's always advisable to start with the pressure buildup first, because I'm using isopropanol in this case, which has a boiling point of between 70 and 80 degrees. So if you start the heating first, you are going to evaporate the solvent, and that can cause a few problems like crystal formation and the clogging of the system. So it's also, once again, a good advice to always start with the pressure regulation first. So I'm just going to put 50 bars and press control. And I would like to wait a few minutes until this pressure is achieved. And after that, while we are waiting for that to happen, I can already put in the 100 degrees C temperature. I am not going to press the on button just yet because I want to build up the fluid pressure first, which takes approximately 5 minutes. And after that, once the heating has been turned on and the 100 degrees has been achieved, the last step that I'm going to take is to press the control button on the hydrogen generation. So once again, internal hydrogen already being selected, I'm going to put 70 milliliters of gas per minute, which is the maximum capacity of the cell. And once the pressure has been built up and the temperature has been reached, I'm going to start the control or the injection of the gas as well. So this takes a couple of minutes, so we'll come back to you when that happens. So now we have achieved what we call the steady state of the instrument. So all of the parameters have been reached and it's stabilized. If we now go to the graph screen, you will be able to see nice and flat lines. Of course, not here in the camera, but when you look at live the screen, we'll be able to display the stable state and stable condition of all the set parameters. And if we go back to the manual operation, now we are ready to start the real experiment. So far, for 10 minutes, I was injecting clean solvent and the hydrogen mixture through the catalyst cartridge to activate its active sites. But that has been going on for 10 minutes at 100 bars and 50 bars of pressure. So now we are ready to start the real chemistry, which is very simple. It just takes 2 buttons, because I'm now going to switch from the solvent to the actual starting material injection. And maybe after 2 or 3 minutes, we can also switch the waste collection to the product. Actually, you can also do it now, because you are just collecting 2 minutes of clean solvent in addition to the already collected material. But if you want to really wait for the material to appear at the end of the flow path, you can wait 2 or 3 minutes. That's the dead volume of the system. And then you can start collecting the product by pressing the product button. That will switch to this flask, which is empty at the moment. That's where we will collect the solution of the product. Now I have been collecting the product sample for 5 minutes, and you can see in the product collection flask that we have a nice and colorless liquid, which is proof that the nitro group reduction has happened quantitatively, because the material has lost its yellow color that's characteristic to the nitro compounds, and we have formed the amine, which is a colorless material. So I've been doing this for about 5 or 10 minutes, collecting approximately 5-10 milliliter sample. And if you're doing a real experiment and you don't know nothing about your chemistry and you want to do a small optimization project, which is just a trial of several different other parameters, you would be able to do it now. So it's possible to set up different parameters during the experiment. You don't have to stop the run, but you can change the parameters during the operation as well. Or you have also the option to stop the experiment But before you do that, I always advise that we do a post-washing cycle as well. So we just clear out all the materials that we injected into the system. And in order to do that, we can just very simply switch back to the waste collection flask. And now you can see we are collecting the material to the waste flask now. And I'm also going to switch from the starting solution to the clean solvent also on the inlet side. And now we have basically initiated the washing. I'm just going to allow this system another 5 or 10 minutes for the new solvent to reach the end of the flow path, and that will signify that the washing has been completed. This is also useful for reactivating the catalyst at the end of the experiment, so you don't have to just do it before the experiment. It's also an option and a good practice to do it after the experiment. So it's very good for the longevity of the catalyst. So in about 5 minutes, I will be able to stop the experiment by releasing the pressure and the temperature. That can happen pretty much at the same time. Maybe it's advisable to start the cooling first in order to avoid the overboiling of the solvent. So if you want to be extra careful, you stop the heating first and then release the pressure to avoid instantaneous evaporation. And after both of those parameters have reached atmospheric and room temperature conditions, you can stop the injection of gas and liquids, and that's basically the end of the experiment. It takes about 15 to 20 minutes from start to finish to do an experiment in these instruments, so that's very useful. That you can immediately see that it's a lot faster compared to batch protocols. Thank you very much for attending today's webinar on the HCube Advance instrument. Before we move on to the questions and answers section, I would like to draw your attention to a couple of further materials that's very useful. We have previous webinars, 3 instances of previous webinars on the basics of flow chemistry. That's available on our YouTube channel, and they can be watched free of charge if you're interested in further applications on what's possible in our other instrument systems, as well as the previous HCubes. And we also have 2 textbooks on flow chemistry applications for slightly more advanced and slightly more detailed applications that's possible under continuous flow conditions. So thank you very much again, and see you in the live question section. Welcome to this live questions and answers sections of the HCube Advanced webinar. We did receive 2 questions to our askthechemist@ThalesNano.com email address. This is still usable, so feel free to send your questions to this email address, or feel free to use the live chat of the YouTube screen. The first question that we already had during the webinar session is, how long can I use a single cat card for? That always depends on the type of chemistry. So every experiment is individual, and you have to experimentally determine the lifespan of every catalyst type, depending on the reaction that you are using. So it's specific. However, there are some general rules of thumb that you can use. If you have some atoms or functional groups or moieties in your molecule that are known to damage the catalyst activity, and they act as catalyst poisons, such as sulfur atoms, that would be a very potent catalyst poison. So maybe after a couple hundred milligrams of transformation, it will already lose some of its activity. And then there are mild catalyst poisons, such as amines and nitrogen heterocycles, that will also slightly decrease the catalyst activity over time. However, there are some tips and tricks to refresh the catalyst. You can run a clean solvent and a hydrogen mixture through the cartridge to reactivate its active sites, and you can do this a couple of times. Again, the number of times depends on the type of reaction, but it's a good trick to refresh the catalyst and reactivate its active sites. Of course, you cannot do this indefinitely, so eventually the catalyst activity will permanently run out. However, it's a generally good rule of thumb that 1 cat cart will be able to transform approximately a few grams to a few tens of grams of material. The second question that we received is, can I use the hydrogen from the instrument to fill an autoclave? The answer is yes. So this is the difference between the previous generation, HQ Pro, and the new generation, the HQ Advance, because now if you use the manual screen of the instrument, it's possible to start each and every individual function of the instrument, such as the pump, the cell, the temperature and the pressure regulation. So if you would like to fill an autoclave, the only thing you will have to do is to leave everything off except the cell, so the hydrogen generation. You can turn it on individually with nothing else turned on, and then you will have to disconnect the front panel tubing at some point and use a tubing and the suitable adapters to connect your H-Cube Advance to your autoclave. There is a small limitation with the time factor because the instrument generates 70 milliliters of hydrogen gas per minute, normal milliliters. So that's quite a low amount compared to the volume of some autoclaves. So if your autoclave is approximately 500 milliliters or maybe a couple of liters, there could be a couple of hours needed to fill the headspace of your autoclave if you want to use it at fairly elevated pressures, such as, for example, 50 bars would take a couple of hours to fill, but it's perfectly possible to arrange that. So I'm looking at the YouTube chat. There are no questions there. So while we are waiting for some further questions, let me quickly mention that our email address, the askthechemist@thalesnano.com, is permanently available. We don't just use it for this webinar. We monitor it daily with my chemist colleagues, and we provide further support. So if you have any questions in the future regarding this instrument or this webinar, or any other applications and any other equipment, please feel free to drop us an email to this email address. We will constantly monitor that, and the usual answer time is less than 24 hours, so we get back to you very quickly with an answer. We also would like to recommend our webpage, that's ThalesNano.com, where you can download further readings regarding the H-Cube Advance, as well as some other instruments. If you're, for example, looking for a scale-up system, we do offer the Phoenix Genie platform for continuous flow hydrogenations on the kilogram per day scale. The recorded webinar material will also be available, so if your colleagues or your friends have missed it and didn't have a chance to view the live webinar, it will be available to rewatch on our YouTube channel. And once again, if they have some questions or you have some questions later when you are rewatching the series, the askthechemist@thalesnano.com email address will be available even then in the future to ask your questions from us. All right, we do have a third question, which is, what is the solvent and acid tolerance of the reactor? So as for solvents, almost all types are completely usable. The only thing that's not exactly recommended, or you have to handle with a little bit of care, is the halogenated solvents, so dichloromethane, chloroform, because that can damage the plastic parts of the system, for example, the membranes and the sealing gaskets of the catalyst cartridges. However, under mild conditions, so if you don't plan to use any elevated temperatures and pressures, the damage is negligible. So especially if you are considering low reaction times, or if you don't plan to use it constantly for certain experiments, in the short run, it's perfectly usable. Just don't forget to wash it after the experiment with a clean solvent. As for the acid tolerance, weak carboxylic acids are compatible with the system. So this is a stainless steel version of the system. So, for example, acetic acids, especially in dilute solutions and under mild conditions, are usable. However, we do offer also the Hastelloy version of the instrument, and that will be able to withstand stronger mineral acids, as well as highly corrosive and oxidative reagents as well. Okay, so as far as I can tell, there are no further questions, so I would like to thank you for joining us today. And feel free to browse all of our materials on our webpage and rewatch the session and write to us to askthechemist@ThalesNano.com. And thank you very much for coming, and have a great rest of your day.